use the power series to expand out terms and write something like, if we look at question 4, this question here, this function, 2e to the x squared x to the half, multiply out that function, expand it into a series form, we get this. So we could calculate what the answer is for this function for up to a certain accuracy. And more than that, we can integrate it or differentiate it. And for some more complex functions, it would be much easier to differentiate this power series, if we look at the answer that you got in the textbook, just differentiate each term separately, than to try and differentiate in something like this, where the x is in the power and it's also x squared. So we'd have to use the function rule on this to work this one out, as well as the product rule, because of the fact we've got the x and a half there. So we could do it, and we've done the calculus about doing that, but it would be much easier to differentiate the power series. So expanding it out to a power series can be a really useful step. Now what we need to do is to look at how this power series, remember as we said at the beginning, this exponential function can be written as, we go back to the start, 1 plus x squared over 2 factorial, and so on. How do we arrive at that? And that's what I want to look at now. I want to look at Maclaurin series, which is here. So if you want to just make a note of this. Okay, so this Maclaurin series, it makes an assumption. It assumes that any function can be written as a power series of the form, it's got some constant, a, it's got some term involving x. This is assuming it's a function where x is the variable, of course, so this would be true for whatever letter we put in here. So for a function where x is the independent variable, there's some constant, there's some term involving x, there's some term involving x squared, maybe some term involving x cubed, and so on, ad infinitum. And if you think about it, it's quite a reasonable assumption to say, well, if we've got an x, there could be something involving an x, something involving an x squared. There may not be a term involving x cubed, and so on. And then what we do is we find out what these coefficients are, these numbers in front of the x and the x squared and the x cubed. And if we find there is no term involving x cubed, then we'll find that d is 0, so that bit's disappeared. So what we need is some way of finding out what these coefficients of x are, a, b, c, and d. And that's what Maclaurin series is all about. And it uses differentiation to do it. What we do is we find the values of the coefficients by getting rid of all the other terms. So let's look at an example. So here's an example. Let's try and find the power series for e to the x, which is what we started with at the beginning of today. So let's arrive at this power series for e to the x. So what we're going to do, as it said on the previous slide, we're going to assume that e to the x, this function that we want to represent, which is in terms of x, can be written as a plus bx plus cx squared plus dx to the 3 plus ex to the 4, and so on. And then what we do is we find the first term, that's this term, the a, by finding the value of the function when x equals 0. How will that help? If we find the value of this function, e to the x, when x is 0, how does that help us to find a? Why x equals 0? Why is that an important? What about these other terms? If x equals 0 in here, Tom, right, what about this term? So in other words, all the terms in this right-hand side, apart from a, will be 0, won't they? So if I let the function equal 0, that gets rid of all the terms apart from the first one. So it allows us to find a. So to find the first term, find the value of the function when x equals 0. So what we're going to do to find the first term, find the value of the function when x equals 0. So write down the value of the function at 0 equals a, because all the other terms have disappeared. But e to the 0, right, anything to the power 0 from the laws of indices is 1. So therefore a equals 1. So we've got the first term in our series, a is 1, so it's going to be 1 plus something. So now let's look at this. What have we done? We've got this series, here it is, and we can find the first term by letting x equals 0. That's fine. And how did it work? Why did that work? Because the first term didn't involve x. So if I let x equal 0, then it's gone. Okay? What we need now is a way of finding b. And this is where the differential comes in. If I find the first differential of the function, and I'm going to use this notation because we're going to finding more than one differential of this. We'll see how it works as we go on. So using the notation f prime to mean the first differential, if I find the first differential, what will that be for this function? If I differentiate a, what will happen? The constant. Differential of the constant is just disappears. Thank you, Mark. What about the differential of bx in terms of x? What will I end up with? B, just b, because the x disappears, doesn't it? What about the next term? Bring the power down, so it'll be 2c, yep, x. Okay, what about the next term? dx squared, and so on, okay? Plus the next term, 4e x cubed, and so on, dot, dot, dot. So we could carry on with the series, couldn't we? So we differentiate it. Yeah, 3dx squared is the third term. You don't square the 2. I don't know what I was thinking of there. By differentiating it now, what we've done is we've got rid of the a, and that's okay because we've already found out what a is. Remember, the whole point of this thing was to find out the coefficients, a, b, c, d, and so on. We found a is 1. Now we're after b. So by differentiating, we get rid of the a, fine, because we've got that already. But what we've done now is we've made b the constant. No term involving b. But all the other terms involve x. So what do you think we do now to try and find out what b is? We let the differential equal, no, what did we do last time? 0. We let it equal 0 because then all the terms disappeared. So we now find let f prime, or find f prime 0. Let x equals 0 and find f prime 0. What's the differential? And so then f prime 0, which equals b. Because all the other terms have gone again. The x is a 0. So, but what is the first differential of e to the x? What is the differential of e to the x? The first differential of e to the x is e to the x. It's its own differential, the exponential function, if you remember. Okay, it's one of those. So, if I now let that equal 0, that's 1, isn't it? So, what's the value of b? 1. So, therefore, b equals 1. Ignore that, Jordan. Therefore, b equals 1. Okay? Now, what do you think we do next to find c? Yep, please. What do we do next to find c? What do we do to find b? And before we did that, we differentiated it. So what do you think we do now to find c? Differentiate it again. We differentiate this. to find c, we find the second differential. So differentiate this. And so on. To find d, I'd find the third differential. To find e, I'd find the fourth differential, and so on. Just keep differentiating. If we look back at this original function, we can see how it works. Look, differentiate once, and it gets rid of the a. Look at this function here. Differentiate once, gets rid of the a. Then I let x equals 0. So that means that all the terms involving x disappear, and I can find b, what we've just done. If I differentiate this function, the differential, then the b disappears, and I'm just left with 2c because the x goes there, so I can find out what c is, and so on. Okay? So find out for me what c is by differentiating this function. So we've got the f prime x equals that. B plus 2cx plus whatever it was, 3dx squared. Done it again. 3dx squared plus 4ex cubed. Now find the second differential. F double prime. Use 2 primes for the second differential and work out what that is. So the second differential gives this, 2c plus 60x plus 12ex squared, and so on. I'm using this notation, Tyler, the double prime notation, rather than, yeah. And now what we're going to do, let x equals 0, right, okay? And so all the terms, except for the first term, disappear. And the differential, when we differentiate e to the x, every time we do it, it's going to be e to the x, isn't it? So e to the 0 is still going to be 1, but now 1 equals 2c. So what does c equal? So now find f double prime when x equals 0. That's just going to equal 2c, but that equals 1 because e to the power 0 is 1. So 2c equals 1, so c equals a half. So we found the value for c. So a equals 1, b equals 1, c equals a half. Yeah. Similar thing. We've got to find d by finding the third differential. Okay. So would you like to do that? Take this second differential here. That's this one, the one we just arrived at, and differentiate that to find the third differential. Yeah. So f triple prime x equals. You could do, couldn't you? And then you go to Roman numerals, actually. Tom, that's a good question. So write down what the third differential is. Find the third differential at 0. And then that allows you to find that d, hopefully. So we work out the third differential, let it equal 0, which that's got to equal 1 because the differential of e to the x is still e to the x, so it's still going to give us 1. So therefore d turns out to be 1 over 6. Well, there is some sort of pattern starts to emerge. So let's take a break there, and then after break we'll have a look at the Maclaurin series in a bit more detail and try it for the sine function.